Well, hello everyone. This is Bill Johnson. I'm going to talk today about the how-to of obtaining breakthrough-elution concentration histories and distributions from source for colloid transport at the continuum scale, but based on pore scale mechanistic trajectory simulations. And so this is using Upscale Continuum in the Party Suite software. And essentially, the ethic here is that there are excellent programs that describe breakthrough-elution concentration histories and distributions from source, such as Hydrus, which then either forward modeling produce breakthrough-elution concentration histories and distributions from source, or take existing data and fit rate constants to describe that data. We can do that with Upscale Continuum, but not as elegantly as Hydrus. So the goal of Upscale Continuum is instead to get under the hood on the rate constants and link, that is, have those rate constants emerge from pore scale mechanistic trajectory simulations involving a force and torque balance, and specifically as determined or developed in TrajHap, that module of Party Suite. And so the idea is to get those rate constants mechanistically. And if you're getting them in order to match those that describe experimental breakthrough-elution curves, you're creating a mechanistic link between those rate constants and the underlying physical chemical processes. So to start, we'll open up Party Suite. As always, you want to open it by right-clicking as an administrator. Otherwise, it will not run properly. And it will pretend to run properly. So you really want to make sure that it asks you for the permission to run as an administrator, and then you know that it will run correctly. So once that's open, maximize the GUI so that you have everything formatted correctly. This GUI has a couple glitches in it. For instance, transport is misspelled. You would think we'd have that right by now. We'll fix that. And it's got a fair number of parameters, but the way it lays out is that the upper left is the pore scale parameters from the trajectory simulation. The bottom left is the continuum scale simulation parameters. And then the middle here is combobulating the pore scale trajectory simulation information to produce the rate constants that are used in the continuum scale simulations. The upper or the middle right here are knobs that we can use for representing what goes on beyond the pore scale to the continuum scale, specifically because the Happel sphere and cell collector is a single, although it represents the overall porous media, it represents a single quote-unquote grain, somewhat non-physically. We don't have an outcome for what happens, for example, for colloids that accumulate in the rear flow stagnation zone of that grain. Do they expel to the bulk fluid, or do they move to a downgradient grain in the near surface? And that's what these knobs do. They control that outcome. So to start, I should mention that the numerics for the pore scale trajectory simulations are controlled there. We can control the time steps there. And that's described in the video related to trajectory simulations. But there are also numerics here at the continuum scale in terms of identifying a time step and a spatial step across the porous media column that one is, and this is one-dimensional, the one-dimensional simulations for a column transport experiment. So I'm going to start, though, with the pore scale. And you can run, one sector I didn't describe here is the middle top. You can run this in forward mode like you'd run Hydrus in forward mode, where you can specify the physical parameters and the rate constants or efficiencies that give you rate constants, as I'll describe in just a bit. And you can do this all without tying back to the trajectory simulations if you wish, just to explore different options. That is done by clicking this edit text box and then populating these other boxes. These boxes will become more clear as you see how it's done based on the pore scale transport simulations. So I'm going to take it from that angle. So to import flux data, I go to the file and I'm going to use the example flux files that I've provided on the web. And these correspond to experiments in porous media done by Shixing Li in 2000, well, the mid-2000s, early mid-2000s. And so they are available on the Party Suite distribution site on my website. They are associated with the MATLAB executables, in this case, Upscale Continuum. We have experiments in glass beads at 6 millimolar, which showed hyperexponential distribution from source. And we have experiments in quartz sand at 6 molar, which showed non-monotonic distribution from source. And so the contrasting behaviors can be captured by these simulations, and so they're available as kind of training material, and also templates for you to make your own upflux files based on your trajectory simulations using TrajHap. So I'm going to start with the glass beads, and so opening that, it will start reading that file. I'm going to show you the contents of these files. So here is the glass bead file. It's simply the text files that are output from TrajHap arranged in this case, in all cases, 4 worksheets. The first 2 corresponding to it, favorable conditions, and the second 2 corresponding to unfavorable conditions. The first one corresponding to attachment under favorable conditions, the second one corresponding to exit under favorable conditions, the third one corresponding to attachment under unfavorable conditions, and the fourth one corresponding to exit under unfavorable conditions. Now, a caveat I need to make clear under the third worksheet, unfavorable attachment under unfavorable conditions, is that I append at the bottom, notice that the attach K, the second column is attach K, which is attach K2 is having attached properly under unfavorable conditions, but we have another option, which is attach K4, where if the colloid is rolling slowly along the surface and we don't want to expend a bunch of numerical effort finally getting it to a rest, we have provisional attachment, and that's attach K4, and I append those under here. Likewise, I append the attach K5 colloids, which are the ones that are retained without attachment, for example, in the rear flow stagnation zone. And those are appended here as well. And they're very important, in fact, for non-monotonic distributions from source, where those slow-moving colloids retained without attachment can move down gradient in the system. And so attach K4 and attach K5 are appended down here without the headers. You only need the one set of headers for these files. You don't change the names of these worksheets because that will prevent the proper reading of these files. So that's what these look like. When you paste data, you paste it in the proper cell A1, and you make sure you're not leaving old data behind. Scroll down to make sure it's not being left behind. As well, you do that with the wizard, with space delimiting to get each bit of information into its cell. Okay, so Upscale is telling me it read in those flux files. And so now it's populated all these fields: collector radius, colloid radius, porosity, injection radius, which you want to keep constant across the 4 worksheets. the average pore water velocity. It will calculate the near surface velocity, near surface fluid velocity, based on those colloids that make it to the rear flow stagnation zone. And so if those don't exist, then it uses 5% of the pore water velocity as the near surface water velocity, and that's a reasonably accurate approximation. These simulations were run with smooth surfaces, so no asperity heights are given here. I guess that's it for the pore scale parameters. So once that's all been read in, we can calculate the efficiencies. And so hit that button. It says note to user. It tells you what it's doing with the attach K246 and attach K5 colloids. It's redefining those for you. And so it's just to let you know those categories. Hit OK. It's calculating those attachment efficiencies, and specifically it's developing the histograms, for example, for the rear flow stagnation zone colloids, their near surface time histograms, coming from the unfavorable data. You've got the attached histograms of residence times before attachment under favorable versus unfavorable conditions. That drives defining the fast and slow attaching population. Same here, but with the near surface times. And you can see that the near surface residence times are much, much greater under unfavorable relative to favorable conditions because of the secondary minimum interactions. So having developed those histograms efficiencies described in Johnson et al. 2018 of the population that enters the near surface, some fraction of them attach fast, some fraction of them attach slow, some of them never attach but are retained in the rear flow stagnation zone, and some of them, in fact the majority here, were re-entrained back to bulk fluid. Now we can upscale those to the rate constants according to the expressions given in Johnson et al. 2018. There's one additional parameter that derives from the fact that the Happel collector is one grain with a fluid envelope. And so there's no defined outcome in that collector for colloids that are retained in the rear flow stagnation zone. Will they be expelled to bulk fluid, or will they move to the near surface of a down gradient grain? And those potential outcomes are discussed in Johnson et al. 2018, as well as Johnson and Hilpert 2013. So for the case of the experiments we're simulating here, these are hyper-exponential, and there was no need to invoke part of the population moving to the near surface of down gradient grains. So I'm not going to make that value greater than 0. And so it calculates those rate constants, and I will use those upscaled values. I will not develop my own through this pathway. And I'm going to perform an implicit simulation, which means that it's really just the fast and slow attachment rate constants that are relevant. The numerics here are set up for our 20 centimeter long columns with 3.6 centimeter, sorry, reading the wrong number here, 3.8 centimeter diameter cross-sectional area. The number of colloids I'm going to use in these simulations is 50,000. The more I use, the slower the simulation, but the smoother the breakthrough-elution concentration histories and distributions from source that emerge. The actual inlet influent concentration was 1 times 10 to the 12th colloids per cubic meter, or in usual terms, it's 1 times 10 to the 6th colloids per milliliter. The total time of the experiment was 12 hours with 3.6 hours devoted to injection of the colloid, which was 3 pore volumes in these columns. And then the remainder, a little more than 7 pore volumes, 7 pore volumes or a little more than 7 hours, was for elution following injection. I'm using a time step of 1/100th of an hour and a spatial step of 1/100th or a centimeter, 1/100th of a meter, a centimeter. And you need to keep an eye on these to make sure that changing these doesn't change your results, right? That's the drawback of numerical simulations, of course, is their dependence on spatial and time steps above some threshold value. I've done that, and so I'm going to go ahead and hit simulate, and this will produce the breakthrough-elution concentration histories and the distributions from source. So it's reasonably fast under these conditions. These are going to be relatively coarse outputs, but they'll give you the idea, because this is really more of a how-to video than a scientific presentation. So it's finished. Hit continue. You can see that the on this scale, the breakthrough plateaus are really quite high, almost indistinguishable from C over C naught of 1. And that's because we had very little attachment on glass beads. But under these conditions is 6 millimolar. But what you can see is that the distribution from source is showing a hyperexponential nature, even despite the coarse output, where there's an initial, across the first few centimeters of the column, an initial decrease that follows roughly log linear trend, but then a relatively flat profile from a few centimeters on, characteristic of experiments under unfavorable conditions. This data is saved wherever you decide to save it. The output directory is called Upscale, output Upscale, and you can decide where you want that to be by clicking on this location. The contrasting condition that I'll show you now is for quartz sand, and let me go dig this up. I'm going to pause this while it's reading. Okay, so it's read in the file, it's read in the numbers. They all match what we had for the glass beads. The only thing that has changed is the medium, which isn't reflected here in any of these parameters. It's reflected in all of the outcomes that occurred in TraChap. And so I'm going to calculate the efficiencies, hit OK. And so now it's got the new set of histograms for the simulations in quartz sand, which, by the way, involves a higher Hamaker constant than glass beads. And so that's reflected in the simulated pore scale transport behaviors. One thing I should mention is that the calculated average near surface water velocity does not show here, it shows down here. And so I forgot to point that out for the glass beads, but it's somewhat lower in the quartz sand. And we have different values now for the different efficiencies in the near surface population. We can calculate the rate constants, and now those are different than what they were for the glass beads. And in this case, actually though, we do need to account for the fact that there's a significant, very significant rear flow stagnation zone population. So 95% of those that entered the near surface ended up back there, whereas in the glass beads, that was not the case. And so we need to do something with them. And I'm going to say that half of them go to the down gradient grains and half of them go to the bulk fluid. And I'm going to recalculate those rate constants based on that. Okay, so I've done that. I'm going to use the upscale values. Continue. One thing I didn't point out is there's also, in addition to, well, the near surface fluid velocity ends up in the rate constants. And so for the rate constant corresponding to the entry of colloids to the near surface in the explicit simulations, that's the only place that rate constant is used, you can choose between the near surface fluid velocity, the geometric mean of that with the average pore water velocity, or the average pore water velocity itself. And I just chose the geometric mean, but I could have chosen any of those three. And so I'm going to use those upscale values, and I'm going to perform an explicit simulation. So now that involves both the fast attachment rate constant as well as the rate coefficient going bringing colloids to the near surface, and then the slow attachment rate constant for those colloids when they're in the near surface. Same parameters for the experiment, so I'm not going to change those. I'm going to simulate and let that roll. So the simulation is just about complete. I'll hit continue. You can see that there's significantly more retention in these quartz sand media, and so the breakthrough curves are dropping with distance. Still not a lot of retention, but more than in the glass beads. And the profiles with distance from the source, from the inlet, is non-monotonic, with most of that non-monotonic profile comprised by attached immobilized colloids, some very small fraction being comprised by near surface non-attached colloids moving slowly down the system. So that's a quick overview of how upscale continuum works and how we use it to explain distributions of colloids from source and their breakthrough elution concentration histories. As always, please contact us if you have questions, if you're using this, if you're interested in using this, and we'll be happy to work with you. Thank you.